This is your presenter, Asloob Mudassar, and I am presenting slide number 16C of the course on atomic and molecular physics. In the today's lecture, I shall be covering fine structure of X-ray spectra and X-ray absorption spectra. These two topics will be covered in the today's lecture, and this is the third lecture of the series on X-ray spectra. Fine structure of the X-ray spectra. K series, for the K series, n prime should be greater than equal to 2, whereas n is equal to 1. You know that n is equal to 1 represents the base level. So for K series, the base level is n is equal to 1. For L series, the base level is n is equal to 2. For M series, the base level is n is equal to 3. For N series, the base level is n is equal to 4. So let's talk about K series. The base level is n is equal to 1, and all the higher states are represented by the quantum number n prime. So n prime should be at least greater than equal to 2. So for the K series, the transitions will take place from n prime equal to 2 to n is equal to 1, giving you K alpha. And n prime is equal to 3 to n is equal to 1 will give you K beta. Similarly, the transition from n prime is equal to 4 to n is equal to 1 will give you K gamma and so on. Similarly, for the L series, we can obtain L1, L2, and L alpha, L beta, L gamma, L delta. So these transitions will take place for increasing value of n prime beyond 3. So when n prime is equal to 3, that is the transition takes place from n prime is equal to 3 to n is equal to 2, then L alpha will be emitted. And when n prime is equal to 4, then the transition from n prime is equal to 4 to n is equal to 2 will give you L beta, and similarly. So you see that I have shown the base levels of all of these series, and I have also shown these higher levels represented by the principal quantum number n prime. There is only one transition between n prime is equal to 2 to n is equal to 1, giving you K alpha, and one transition for the K beta, which is due to the transition from n prime is equal to 3 to n is equal to 1. So you see that I have explained K alpha and K beta, but of course with even more higher principal quantum number n prime, you can observe K gamma, K delta, and so on. If there is a coupling between orbital angular momentum and spin angular momentum, which we call as spin orbit coupling, then each level for a given n is split into several components, resulting in several transitions called fine structure. You see that I have delivered a detailed lecture on fine structure in one of the previous lectures. You can go through that lecture if you are not understanding fine structure. But let me explain to you here very briefly that in the fine structure, there is a coupling between two quantities, orbital angular momentum and spin angular momentum. Or you more precisely, you can say that the coupling between orbital magnetic moment and the spin magnetic moment. Or equivalently, orbital angular momentum or the spin angular momentum. So if there is a coupling between these two quantities, then which we call as a spin orbit coupling, then due to this coupling there will be a further splitting of each levels, and those splittings are called the fine structures. So in the next few pages we shall see that the K series, that is the K shell, is not splitted. That is, the K level is not splitted, it remains a single level, whereas there will be a splitting of L levels, there will be a splitting of M level, there will be a splitting of N levels. For example, the L level will be split into 3 levels. M level will be split into 5 levels due to spin orbit coupling or due to fine structure. But the K series will remain, but the K level will remain a single level. This is what we shall see in the next few pages. In many electron atoms, different elliptical orbits correspond to different L values, and there is an associated Coulomb potential which experiences different degrees of screening. The orbital degeneracy is lifted naturally. So in the past, I have also discussed the elliptical orbits in much greater detail. To each elliptical orbit of the electron, there is an associated quantity which we also called as orbital quantum number L. And different elliptical orbits will face different Coulomb potential because of the different degrees of screening experienced by different electrons located in different shells. And due to that one, due to different degrees of screening and due to the elliptical orbits of the electrons, and due to different values of L for different orbits, the orbital degeneracy is lifted naturally. That is, the energy of the electron in different orbits now becomes dependent upon the value of the quantum number L. And this is referred to as the and this is because of the degree of screening, and I have discussed this one in much greater detail in one of the previous lectures. The actual fine structure is due to spin orbit coupling. So you see that when I say that for the elliptical orbits, the energies of an electron in an elliptical orbit, besides the principal quantum number n, also depends upon the orbital quantum number L over here. And now this L is the orbital quantum number, also known as the orbital quantum number, but this is associated with the Coulomb potential. And because of different screening, because of different degrees of screening faced by the electrons. So the energy due to the elliptical orbits, the energy of the electrons depends on two quantum numbers. One is the principal quantum number n, and the other is the orbital quantum number L. That's why we say that the orbital degeneracy is lifted. So there will be a splitting of states. But you know that we don't call the splitting of such states as the fine structure. The fine structure splitting is actually associated with only when there is a coupling between the orbital quantities and between the spin quantities. And then there will be a difference of energies. That is the energy depends, that is the energy is splitted because of the spin orbit coupling. And that splitting of energy based on spin orbit coupling is referred to as the fine structure. The actual fine structure is due to spin orbit coupling. And the splitting energy increases rapidly with the nuclear charge. That is to the fourth power of the nuclear charge. That is, for heavier atoms, there will be more or significant value of the spin orbit coupling. That is, the levels will be well separated for higher values of the Z value, for the higher Z values or for the heavier atoms. For U, that is for the uranium, the spin orbit coupling amounts to of the order of 2 kilo electron volt. So you can notice this magnitude, which is significantly higher for the uranium atom. Structure of X-ray spectra can be understood if a missing electron or a hole in a full shell is equivalent to a single electron in an empty shell. That is, you see that in the production of X-rays, what we do is that we remove an internal electron, an inner electron, for example, an electron from the K shell or an electron from the L shell, etc. So when such an electron is removed from the inner shell, a hole is created. A vacancy of electron is created, which we call as the hole. A hole is created, which can be treated as equivalent to a single electron in an empty shell. So if we treat such a hole as a single electron in an empty shell, then of course we can explain the X-ray spectra. X-ray spectra can thus be understood similar to the spectra of alkali atoms as a single electron or a single hole spectra. And you know that alkali metal atoms, I have also discussed alkali metal atoms in much greater detail and discussed their spectra in also much greater detail. So if you want to know the spectra of the alkali metals, you should consult my one of the previous lectures on the topics. Terms in the X-ray spectra are characterized as terms in alkali spectra by quantum numbers of one electron system. So you see that, as said earlier, I shall be explaining the spectra of the X-rays using a model of one electron system placed in an empty shell. So let's talk about the K shell. For a K shell, the value of the principal quantum number n is equal to 1 because n is equal to 1 provides a base level for the K shell. So when n is equal to 1, the orbital quantum number is 0 and the spin quantum number s is always equal to half because we are talking about a single electron. And for the K shell, since n is equal to 1, so L is equal to 0 is a must condition. And J, which is the total quantum number of such an electron, will be equal to the J is equal to the mod of L plus minus S. So 0 plus minus half will give you half. So J, that is the total quantum number of the atom, is equal to half. So here we are considering the K shell to be consisting of a single hole vacancy, which we are treating as a single electron placed in an empty K shell. So that's why we have written these set of quantum numbers. N is equal to 1, L is equal to 0, S is equal to half, and J, the total quantum number of that atom or that shell, is equal to J is equal to half. And the state is designated by 1, which is due to principal quantum number. 2 is the multiplicity. S is the term symbol corresponding to L is equal to 0. And this half is due to J. So 1, 2 as half is the term state for an electron which is removed from the K shell. For such a K shell, we can write down the term state as 1 and 2 as half. This 2 is the multiplicity, and the multiplicity is equal to capital M is equal to 2 times S plus 1. Since S is equal to half, so 2 times S is equal to 1 and plus 1 due to multiplicity will give you 2. So multiplicity capital M is equal to 2S plus 1. So will give you a value of 2. So I have written multiplicity 2 as a superscript before the symbol S. Selection rules for optical transition. So you see that I am using the same selection rules as applicable to the alkali metal atoms, that is delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. These will be the selection rules in order to explain the X-ray spectra. Now let's talk about the level 2. That is, you have removed an electron from the shell L, inner shell L of the system of the heavy atom. And for the L shell, we have n is equal to 2. So when n is equal to 2, there are two possibilities for the quantum number L. L1 is equal to 0, L2 is equal to 1. And you know that it means that for n is equal to 2, there will be a possibility of accommodating two electrons, one with the L is equal to 0, the other with the L2 is equal to 1. And for this electron, which is L1 is equal to 0, the spin quantum number S1 is equal to half. And for L2 is equal to 1, the spin quantum number of the electron is again half. So S2 is equal to half again. And J1, which is the total quantum number of this electron having L1 is equal to 0, S is equal to half. The J1 is equal to L1 mod of L1 plus minus S1 will give you J1 is equal to half. and J2, which is equal to the mod of L2 plus minus S2 will give you two values, because 1 plus half will give you 3 half and 1 minus half will give you 1 half. And the term symbol corresponding to L1 is equal to 0 is capital S, and the term symbol corresponding to L2 is equal to 1 is capital P. The multiplicity for this system, M1 is equal to 2, S1 plus 1 is equal to 2. And the multiplicity for this system, which is M2 is equal to 2, S2 plus 1 is again 2. Because S1 and S2 for a single electron are S1 is equal to half and S2 is equal to half. So you see that the energy terms can now be written as, for the electron with the parameters L1 is equal to 0, S1 is equal to half, the energy term will be expressed as 2 and 2 as half, where this 2 is actually the principal quantum number, and this 2 as a pre-superscript is actually the multiplicity which we have calculated as M1 is equal to 2, and S is the term symbol, and this 1 half is actually the total quantum number J1. Similarly, the energy term for this electron is equal to 2p 3 half and 1 half, where 3 half and 1 half are the values of the total quantum number J2 of the atom. Now you see that for the M shell of the electron, if an electron, for the M shell of the electron, which has a value of a principal quantum number n is equal to 3, for such an electron we can write the energy terms as 3 2 s half, 3 2 p 3 half and 1 half, and 3 2 d 5 half and 3 half. And these energy terms can similarly obtained as the energy terms that I have obtained for the value of n is equal to 2. The X-ray energy spectrum for platinum PT Z is equal to 78 is shown on the next page. That is this one. Energy spectrum due to platinum Z is equal to 78. I shall be coming back to this one. The X-ray energy spectrum for platinum with the symbol PT and Z is equal to 78 is shown on the next page. K alpha 1, K alpha 2 are similar to D1 and D2 lines of the sodium atom. The separation between the terms is not to the scale, because you see that I have used an expanded scale from 0 to minus 20, so that I can explain these spectral lines with a greater separation. And you know that beyond minus 20 kilo electron volt to minus 70 kilo electron, the scale is compressed, so that this figure can be accommodated on the page. The separation between the terms is not to scale. The separation between 2s half and 2p 1 half results from the variation in screening. So the separation between these two terms, that is 2s half and 2p 1 half, is because of the variation in screening. And the separation between 2p 1 half and 2p 3 half increases with the nuclear charge Z, or with the atomic charge Z. So I have explained the separation between 2s half and 2p half, which is due to a variation in screening. And the separation between 2p 1 half and 2p 3 half, this separation will increase from atom to atom. The heavier atom in the heavier atoms, the Z value is larger, so the separation between 2p 1 half and 2p 3 half will be greater. Now let me explain this spectrum. I have the K shell due to principal quantum number n is equal to 1. Then I have the L shell due to the principal quantum number 2. These are three values, L1, L2, L3. Then I have the M shell due to the principal quantum number 3. and the value of this will split into 5 levels: M1, M2, M3, M4, M5. The energy of these levels where they are located is shown on the left hand side. So you see that on the right column, I have shown three quantum numbers: n, principal quantum number n, orbital quantum number L, total quantum number J. And you know that when the principal quantum number n is equal to 3, the possible values for L are 0, 1, and 2. And the values of J will be when you have when you come and you know that when you want to find the value of J, you need to have the spin quantum number of the electron, which is S is equal to half. So J, which is equal to mod of L plus minus half, and you know that if you combine those one, you will get these terms. So the values of J that you will obtain by combining the orbital quantum number and the spin quantum number, you will get corresponding to n is equal to 3, L is equal to 0, you will get J half. And when n is equal to 3, L is equal to 1, you will get again J half. When n is equal to 3, L is equal to 1, you will get J is equal to 3 half. Similarly, when n is equal to 3, L is equal to 2, you will get J is equal to 3 half. And when n is equal to 3, L is equal to 2, you will get J 5 half. So these are the possible values of J that I have written. And the term symbols and the energy terms have also been written. That is, for M1, the energy term is 2s half. For M2 level, the energy term is 2p1 half. For M3 level, the energy term is 2p3 half. And for M4 levels, the energy term is 2d3 half. And for M5 level, the energy term is 2d5 half. These are actually the fine structure of the level M. Similarly, the fine structure of the level L is indicated by the three levels L1, L2, and L3. And similarly, you can explain these three levels, like the one I have explained, the M levels. Now you see that let's talk about the K series first. You know that for the K series, I have shown these transitions, and these transitions must obey the rule. What is the rule? The rule is delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. So these are the rules. J to J transition will not be allowed. But the transition from J is equal to, for example, 1 half to the J is equal to 1 half of the lower level is allowed. Because when J is 1 half and the lower level has also the same value, J is equal to 1 half, then the difference between them is 0. That is allowed, but the difference of J is equal to 0. That is, the transition from J is equal to 0 to J is equal to 0 will not be permissible. So you see that I am explaining the spectrum of the X-ray under these selection rules, that is delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. So I am not explaining each term, so you must convince yourself with the selection rules that these are the allowed transitions. So you see that I am going to show you this green transition, for example, which we have labeled alpha 2. Then the red transition from L3 to the base level of K transition, which is labeled as alpha 1. Then the transition from M2 level, from the M2 level to the base level, to the K base level, will be represented. That transition is shown in blue and represented by beta 3. Similarly, the transition from M3 to the K level will be represented by beta 1. Actually, these are the historical labeling. In the very beginning, when this X-ray spectra was observed, these labels were given. Now these labels don't have any importance, because everything about the quantum physics and about the atomic physics is known to us. So these are just the historical labels that I have also adopted and shown over here. And you know that here H nu, Gr stand for the ground. So H nu, which is the photon, which can be used to knock out a K electron, that is a K ion electron can be ionized using the energy which is equal to H nu ground. And this is indicated by a bold arrow shown in black. So if you provide this much energy to an electron in the K shell, the electron will be removed in the continuum region. That is, the electron will be ionized, and that energy will be equal to H nu ground. And this energy will be equal to the K edge of the electron, K edge of the series. So you see that K edge of the series, that is if an electron is jumping from the outermost shell, for example, to the valence shell of the atom, to the K shell of the electron to fill the vacancy of the electron there, then that energy will be the maximum energy and will be referred to as the K edge of the series. So K edge is actually the final element of the series with the maximum possible energy. And here in this picture, it will be equal to the energy expressed by this black arrow shown in bold, and the energy is equal to H nu Gr. So if an electron, so you see that you have K series will be labeled as K alpha, K beta, K gamma, K delta, and so on. And so this will form a series of K series. This is referred to as the K series. The last element of the K series, which will correspond to the maximum value of energy, will be equal to the energy when the electron from the valence electron jumps to the K shell to fill the vacancy of the electron. And the energy that will be related in the form of X-ray gamma will have an energy equal to H nu ground, and that will be the maximum energy which will be referred to as the K edge. So now let's discuss the L1, L2, and L3, these levels. You see that I have also shown the transitions from different M levels to these L1, L2, L3 levels, obeying the same selection rules, that is delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. So I have obeying those selection rules, I have shown these transitions. And you know that these transitions have also been labeled as beta 4, beta 3, eta, beta 1, L, alpha 2, alpha 1, L1, L2, and L3. So L1, L2, L3 are the series limits. That is, you know that L1, the series limit starts from L1 to the continuum. Similarly, the series limit L2 starts from level L2 to the continuum. Similarly, the series limit L3 starts from the continuum, starts from the level L3 to the continuum. So it means that if an electron jumps from the valence shell to the level L1, it will emit an energy in the form of X-ray quanta equal to the energy provided to ionize an electron from the L1 shell. So that is why such a quanta will be referred to as the L1 edge. Similarly, when an electron from the valence orbit or the outermost orbit jumps to fill the vacancy in the L2 shell, then of course the energy of the quanta that will be emitted during this transition is referred to as the L2 edge. And this L2 edge is the last element of the L2 series. And L2 edge will be equal to the energy which is required to ionize an electron from the L2 subshell to the continuum. So similarly, the case for other. Similarly, you see that you can also explain the M series, but I have not shown the transitions from the M series because otherwise I have to include the upper level, that is the ON level, and of course the figure will then be more complex. So you see that with this simple figure, I have explained the historical diagram of this X-ray spectrum, in which I have shown the K series I have shown the L series, different components of the L series, but I have not shown these series in full. Some selected lines of the series have been shown. So all the transitions from the higher level to the K level, to the base level of the K level, will form a K series. And all the transitions from the higher levels to the L1 level will form the L1 series. And from the higher levels to the L2 will form the L2 series. Similarly, the transitions from the higher levels to L3 level will form the L3 series. And the maximum energies corresponding to these L1, L2, L3 levels will be referred to as the L1 edge, L2 edge, and L3 edge respectively. And similarly, you see that for the K shell, I have given the set of quantum numbers, and 1 is the principal quantum number, L is the orbital quantum number, 1/2 is the value of the total quantum number J of the atom, and 2 as a 1/2 is actually the energy term for the K shell. So you see that I have explained all these transitions, and with the use of the historical symbols used to designate these transitions. But you know that in the today's spectroscopic data, these levels are not explained with the conventional symbols, but you can level them or explain them as K alpha, K beta, K gamma, K delta, and so on. Similarly, for the L series, you can refer to them as L alpha, L beta, L gamma, L delta, and so on. Similarly, for other M series, N series, O series, etc. Now you see that now I am going to discuss the absorption spectra of the X-rays. X-ray, when incident on a material, are absorbed and scattered. So you see that when you shine an X-ray on any material, the material can absorb the X-rays and can re-emit the X-rays or can scatter the X-rays. Ignoring scattering, the transmitted intensity, since we are talking about the absorption spectrum, so you see that we shall measure the absorption, we shall measure the transmitted intensity through the sample. And if we are considering the transmission spectrum, then of course we shall measure the light which is absorbed by the sample and re-emitted in different directions. So since I am talking about the absorption spectrum, so I shall be measuring the intensity which is transmitted through the sample. So ignoring the scattering, the transmitted intensity through the thickness X of a material with extinction coefficient mu is given by. So you see that here I am talking about a material of thickness X, and the extinction coefficient of the material is mu. And the relationship is I is equal to I naught e to the power minus mu times X, where I naught is the initial intensity of the X-rays entering into the sample. That is, when X is equal to 0, the intensity of the X-rays entering into the sample will be I naught. And this I on the left hand side is actually the intensity when the X-rays has traveled a distance equal to X in the material. And mu is actually the extinction coefficient of the material, which will due to which one the intensity of the X-rays will decay. So you see that if you want to calculate the intensity I, at what distance X the intensity becomes equal to half, that can be calculated by choosing X is equal to, by calculating the value of X for which the value of intensity becomes half. So putting this capital I on the left hand side equal to I naught by 2, and then solving this equation for the value of X or for the value of D, that X can be replaced by the value of D, then you can calculate the distance D within the material at which the X-ray intensity entering into the material will becomes equal to half. So I naught is the incident X-ray intensity, and capital I is the intensity usually specified for the thickness. After the material after the X-rays has traveled a thickness X within the material. So you see that it is conventional to find out this X for which the intensity becomes equal to half. So using X is equal to D. So using D instead of X and putting this capital I is equal to I naught by 2 as shown over here in equation number 9. I have I naught over 2 is equal to I naught e to the power minus mu times d. I can solve this equation for the value of d, which will give you the final result, and d will be equal to mu inverse multiplied by the log of 2. So if you know the value of 2 for a material, you can find out the distance within the material, which will reduce the intensity entering into the material by a factor of half. So D depends on the material, mu, and the energy of the X-ray quanta. So you see that in this expression, the final expression in equation number 9, D is depending upon the value of mu inverse. Okay, and this is what I have written, that D depends upon the material, that is upon the value of mu. But the D that depends upon the value of X-ray is not evident in this equation. Of course, it is quite obvious that if X-rays are more stronger in energy, they will penetrate more into the material. This is quite obvious. And I am going to give you some numerical data. V naught is the accelerating potential for the electron shown in kV. And in the middle column, I have D, which is the thickness into the material by which the intensity of the X-rays will become equal to half, or reduced by a factor of half. D is shown in centimeter for the material of aluminium. Similarly, in the last column, in the rightmost column, D is again shown in centimeter, but for here I am going to show the value of D in centimeter for the material of lead, shown in PB. So you see that. So if you multiply, if you put E within K and V, you will get the energy of the electron in keV. So 10 keV is the energy of the electron, and the energy and the electron with the energy of 10 keV will penetrate a distance of 1.1 into 10 to the power minus 2 centimeter into the aluminium, and it will travel a distance of 7.5 into 10 to the power minus 4 centimeter into the lead with intensity of X-rays becomes equal to half. So again, you know that these distance D is actually the distance by which the intensity of the X-rays entering into the material becomes equal to half. So if an X-ray, if an electron is entering with an energy of 100 kilo electron volt, it will penetrate a distance of 1.6 centimeter into aluminium, and it will enter a distance of 1.1 into 10 to the power minus 2 centimeter into the lead. Mu is the sum of scattering and absorption. When scattering is ignored, mu becomes a function of the absorption alone. The dependence of mu absorption on quantum energy, that is the spectral distribution of absorption spectra, is shown on the next page. That is how the behavior, that is the behavior of mu absorption as a function of the energy of the X-rays entering into the material, which we refer to as the spectral distribution in the absorption spectrum, is shown on the next page, where the emission spectra at various excitation energies are also shown for comparison. So let me show you the figure giving you the spectral distribution of absorption spectra. This is the figure. At the top, I have the absorption spectra shown in A, and you know that here I have shown different M edges. These are the M edges. I have also shown the L edges. 3 L edges I have shown, L3, L2, L1. And similarly for the absorption coefficient, the plot of the absorption coefficient versus the frequency nu of the spectrum, I have also shown the K edge. So these are the edges, and you know that these edges correspond to the energy required to ionize an electron from the K shell. So K shell corresponds to the energy which is required to remove an electron from the K shell. L1, L2, L3 are the edges corresponding to L1, L2 and L3, and these corresponds to the energy required to remove an electron from L1, from L2, from L3 respectively. And these frequencies have also been given as new L1, new L2 and new L3. Similarly, for the M, I have shown these edges M4, M3, M2, M1. These edges have been shown, but I have not labeled those edges because of the smaller space available for this diagram. And again, these edges will correspond, these M edges will correspond to the energies required to move electrons from these levels, that is from the M level, M1 level at the top, then from M2 level, then from M3 level, then from M4 level, then from M5 level, etc. And on the left of the M level there is N level. I have not, because the spectral resolution of the system is not very high, so for the N levels I cannot see any edges over here. So the edges are very prominent for the L1, L2 and L3. That is, the L edges are very prominent, and of course there is only one edge for the K level, for the K shell, and that level is also very prominent. And you notice that with these K edges the absorption coefficient is very high. And if you notice a region between in the L edges, between the L edges and the K edges, you see that there is a continuation of these absorption coefficient falling continuously to the minimum value, towards the minimum value. So you see that this is the level in which the energy of the photon that you are going to excite different levels of the atom, or you see that will not match, and the electrons will not be ionized in this region, but the electrons are only sent to the outermost to the higher shells, but not ionized. And due to movement of the electrons from the inner shell to the higher shells, or maybe the movement of the outermost shells to even higher shells, you see that the edges are not obtained, because the edges will only be obtained when the electrons are removed from these shells. Otherwise the spectrum will be continuum, because this continuum spectrum will not allow you to observe any edges in this region, because in the absorption spectrum these edges or any variation in the region between the L shells and between L edges and the K edges is not observable. And you see that below that one, I have shown the emission spectrum intensities of the emission spectrums of different K, of the K series, of the L series, of L series, etc. M series are not shown over here. But I shall be explaining this one, that where are the M series located. So absorption spectrum of the series is shown over here in the part A, whereas in the part B, C and D, E, the emission spectrum are shown with the different values of the energies, which I shall be explaining in a minute. So you see that so far I have explained the first paragraph. The second paragraph, the plot of mu platinum versus the frequency nu is plotted, giving a comparison of X-ray absorption and emission spectrum. So the plot of mu PT, mu platinum versus frequency nu is plotted, giving a comparison of the X-ray absorption and emission spectra. The same over here. The top, at the top we have the absorption spectra, and B, C, D and E represents the emission spectra. And this plot is for the platinum. Z is equal to 78. The spectrum consists of primarily of superimposed absorption edges. In the spectrum, you can see that there are superimposed edges. For example, these are edges. L1, L2, L3, these are the edges I have shown, and I have also shown you the K edges. So you see that edges mean that the K electron has been ionized. So that's why we get a K edge, because all the other electrons in the outermost, in the surrounding shells, will come to fill the vacancy of the K electron, and then of course a peak is observed in the absorption coefficient. Similarly, L1 and L2 or L3 are the edges corresponding to the level that an electron from the L1 shell has been removed or ionized. Similarly, the edge corresponding to L2 is because an electron from the L2 shell has been ionized, and similarly the L3 edge will correspond to the movement or the ionization of an electron in the L3 level. So the edges correspond to the ionization of those levels, but where the ionization will not occur, you will observe a continuously falling value of the absorption coefficient. You see that for the transmission spectrum, I am observing different peak values, different spectral peaks imposed over the continuous spectrum. So here the continuous spectrum may be treated as the Bremsstrahlung radiation. And on top of that one, you have the K series, for example. These are the K levels. For example, this is K alpha, this is K beta, this is K gamma, this is K delta, and so on. And then finally, you have the dotted line representing a K edge. And you know that on this one, for example, as indicated by the arrow, you have the series L1, L2, and L3. So these will represent, these four, for example, lines will represent the L1, L2, L3 series. And these lines on the left hand side most may be representing the M series. So you see that I have indicated the L1, L2, and L3 series in the plot labeled with B, and in the plot labeled with C. And similarly, the series L2 and L3 are present in the plot of D, but the series L1 is not present. Similarly, you can notice that the K series is present in the plot of B, whereas the K series is not present in the plot of C. Similarly, the plot of series L2, L1 is not present in the series of L2 and L3. Similarly, in the final plot labeled with E, the only series which is present is the L3 series. And you see that I have shown the energies over here. In the B series, the energy of the electron represented by EV is greater than or equal to h nu k. That is either greater than the energy required for the K edge, that is for the ionization of electron from the K shell, or may be greater. So the K electron is ionized, and so a K series is observed. And when the K electron is ionized, we can also observe the transitions at the L1 levels, because it might be possible that for the K series, the transitions is from the L1, L2, L3 levels, and also from M1, M2, M3 levels to the K level. So a K series is obtained. So you see that when the vacancies are created in L1, L2, and L3 levels, of course, to fill these vacancies, the transitions from the M levels and the transitions from the N levels and the transitions from the O level may take place, and then of course L series is obtained. Similarly, we can obtain the M series. But you know that if in the C plot, the value of the electron is greater than the value of the new L1 but less than H nu K. So H nu K is the energy required to obtain the K edge or to ionize the K electron in the atom. So you see that if our electron energy is less than the K is less than the energy required to ionize ionize a K electron, but greater than so that it can ionize an L1 electron, then you will see that you will observe the series L1, L2, and L3. The higher series can also be observed. But you see that here I am just concentrating only on L1, L2, and L3. You may consider the other transitions to be coming from the M1 series. Now let's discuss the D plot in which the energy of the electron is greater than or equal to H nu L2. That is an electron from the level L2 can be ionized, but the other levels, that is the K level and the L1 level, cannot be ionized with this energy of electron given in D. Since an electron from the L2 level can be ionized, so you can observe only the L2 series or the L3 series or even the M3 or even the M series can be observed in the plot of D. Now in the plot of E, you have the electron energy greater than H nu L3. That is, the electron energy is sufficient to ionize an electron from the L3 level. So you can observe the L3 series only. Or even if you can observe the M series and N series, but you see that provided the resolution of your instrument is very high. If the resolution is poor, at least you can observe the series from L3 level. So you see that I have explained why some series are present and why some series are not are missing using the energy of the electrons as shown for the part B, C, D, and E, etc. And you know that these series levels or these series terms shown as perpendicular lines are actually at the top of the X-ray Bremsstrahlung radiations. Now you see that I have explained the spectra. Now I am going through just what is explained there. For example, in the plots from B to E, emission spectrum of the platinum at various excitation energies is given. Kappa series lacks in C to E, L1 lacks in D to E, L1, L2 lacks in series E. And you know that the reason is what I have explained. At absorption edges, you see that I have shown the absorption edges over here. For example, L1, L2, L3 are the absorption edges. Similarly, the absorption edges corresponding to K edge is also shown. And the absorption edges corresponding to M level is also shown but not labeled. So you see that at absorption edges, absorption coefficients jump to a higher value at a specific quantum energy. The edges corresponding to the series limits for K, L, M series, etc. And these edges, you know, that are the limits of the K series, L series, M series, etc. Subshells also appear as edges. You know that the subshells, for example, the L shell has been converted into 3 sub-levels. So you see that L1, L2, and L3 may be referred as the edges corresponding to the sub-levels. Absorption cross-section of lead for X-ray in the region of L and K edges is shown. I am not covering the whole range, but just I am covering the range for the lead in the range so that I can cover the L and K edges. And you know that when I am talking about L and K edges, it means that the energies of the electrons is such that it can ionize the electrons from the L shell and also from the K shell depending upon the energy of the electron. The absorption coefficient is expressed in terms of the absorption cross-section of an atom, and the plot is shown. So you can see this plot. On the vertical side, I have plotted absorption cross-section of the atom in centimeter square. And on the horizontal axis, I have shown the energy of the electron in kilo electron volt, ranging from 0 to about 1000 kilo electron volt. And the absorption cross section in centimeter square is shown as 10 to the power minus 2 to 10 to the power minus 19 along the vertical axis. So you see that when you increase the energy of the electron from 0 keV to a value of approximately 10 kilo electron volt, you will see that L electron in the sample is ionized, and that's why we observe the L edges. So this indicates that what is the binding energy of the L shell, what is the binding energy of the electrons in the L shell. So this explains the structure of the shells. So you see that here we know through this absorption spectra that when the electron energy approaches nearly 10 kilo electron volt, then of course an L electron, that is an electron in the L shell, is ionized and an L edge is detected. And when the energy of the electron increases beyond the value of 10 kilo electron volt, then of course you will see that there is a fall of the absorption cross section of the atom, because there no edge is there, that is no electron is removed in this region. And you see that at about a value of 88 kilo electron volt of energy of the electron, a K edge is observed. So you see that K edge occurs at a value of 88 kilo electron volt of the electron. It means that when the energy of the incident electron matches with the 88 kilo electron volt, then of course a K electron, that is an electron from the K shell, is ionized or removed, and a K edge is detected, which is observed by an increase in the absorption coefficient in the absorption cross section of the atom. But when the value of the energy is increased beyond the K edge, then of course no other edge is observed, because K level is the lowest level, no other edge will appear there. So position of K edge is at 88 kilo electron volt, and this is the energy which is required as the work done in removing the K electron. For lead, Z is equal to 82, and for the ionization of K electron, we have this relationship, that is delta E is equal to Z effective square multiplied by 13.6 electron volt, where 13.6 electron volt is the energy required to ionize a hydrogen electron. And to that one, you can multiply it by Z effective square to find out the energy required to ionize the K electron, or an electron from the K shell. But you know that delta E is given by the square of 82 minus S for the lead, because for the lead the value of capital Z is equal to 82, and S is the parameter related with the screening effect. So this is a screening parameter. So delta E can be written as the square of 82 minus S times 13.6 electron volt. You can compare the two delta E expressions and you can find, because delta E is also 88 kilo electron volt, so you can compare these two delta E expressions and you can find out the screening parameter, which is equal to S is equal to 1.6161. So it means that you can also determine the screening parameter this way, and Z effective is the effective nuclear charge. So you see that through these edges, you can find out the binding energies of the electrons in the L shell and for the of the binding energies of the electron in the K shell. So the structure of the atoms, that is the structure of the shells and the subshells, can be explained through the absorption spectrum of the samples of the heavier atoms. For X-ray absorption by an atom, an electron is excited from an inner shell into a less strongly bound state. For X-ray absorption by an atom, an electron is excited from an inner shell into a less strongly bound state. So you see that here I am not talking about the ionization of that state, because ionization will mean that if you ionize an atom, if you ionize a particular electron in a particular shell, then you will observe an edge corresponding to that shell or corresponding to that subshell. But if you excite an atom, not you are here, you are, I am not talking about ionization, but just excitation. So if an electron is excited from an inner shell into a less strongly bound state, not ionizing but exciting to a less boundary state, neighboring shells are already occupied, and discrete absorption lines and discrete absorption lines are already occupied, and discrete absorption lines due to transition from one shell to another shell are scarcely observable. That's why you see that in this region, that is in the region between the two edges, where the electron energy is used not only to ionize an atom, but to just excite an atom to higher outer states. And you see that in this region, no absorption peak is detected, but only the transitions are detected. The transitions which are due to the transitions which takes place between different levels will be represented by this attenuation of the absorption coefficient, and there is no particular level that we can detect in this region. That's why I have explained over here, that is the neighboring shells all already occupied, and discrete absorption lines due to the transition from one shell to another shell are scarcely observed. So here we cannot observe the discrete absorption lines, cannot be observed, and the reason I have given. There is a continuum of free states beyond the series limit. So you see that I am talking about in this region where there is a continuum, and we don't have any edge peaks over here, and we don't have edges over here. This is the continuous region. So there is a continuum of free states beyond the series limit, into which the absorption electron can be lifted. Absorption is usually associated with ionization, and absorption spectra are the superimposed series limit continuation of the various shells and subshells, referring to figure 22 on page 22. So you see that in the absorption spectra we have edges, K edges, L edges, M edges, which are superimposing on the absorption coefficient spectra, and otherwise without the presence of these edges there will be a continuum of states, and the absorption spectra will attenuate continually with the increase in energy of the electrons, of the incident electron actually. Absorption edges occur when X-ray quantum is sufficient to allow an absorptive transition from a lower shell into a continuum. From a lower shell into a continuum mean that is the ionization of electron in those shells. At a frequency nu, which is smaller than the new edge. You know that new edge is the frequency that corresponds to the edges. For example, for the K edge, the new edge frequency is the highest, has the highest value. So at a frequency less than the new edge, electrons in the outer shells are released. That is, electrons in the outer shells are ionized. Not the inner shells, but the outer shells. And that's why when the electrons in the outer shells are ionized, you observe a region, this, between the edges. This will correspond to the ionization of the outer electrons. So at a frequency less than the new edge, that is the less than the new edge of the electrons in the outer shells are released, that is ionized, and when nu increases, even the k electrons are also released, that is ionized. So if the energy becomes equal to the new edge or greater than the new edge, then of course the k electrons are also ionized. And at this point, the mu absorption increases abruptly. So when the inner electrons are ionized, you can only observe the edges there. And when the outermost electrons are ionized, then you don't observe any edges there. So the edges can only be associated when an electrons from the inner shells are removed or ionized. The fine structure of the absorption edges is further evidence for the existence of shells and subshells. So you see that the fine structure, that is due to the fine structure, we have L1 edge, L2 edge, L3 edge, and similarly we have 5 edges due to M shell, in the M shell, and this is due to the fine structure. So we can, using the fine structure, we can not only obtain the edges corresponding to the shells, but also edges corresponding to the subshells. So the fine structure of the absorption edges is further an evidence for the existence of the shells and the subshells. There is one K edge, but 3 L edges and 5 M edges. If spectral resolution is better, it is possible to detect effects of chemical bonding on the energies, and the fine structure of the absorption edges can be explained further. And you know that we can also explain the chemical bonding provided the spectral resolution of our device is improved. Then the effect of chemical bonding can also be noticed on the absorption spectrum. Aside from the edges, frequency dependence of the absorption coefficient is essentially expressed by. So you see that we are excluding the region of the edges, then mu absorption can be defined as nearly equal to z to the power x divided by the cube of h nu. And x will range in the range, and x ranges from 3 to 4. You can simplify this expression as given in equation number 11, that mu absorption can be written as of the order of lambda to the power 3 and z to the power x. Here I have omitted some constants. As lambda decreases, mu absorption also decreases. Penetrating capability of X-rays. The penetrating capability of X-rays increases, which also increases with accelerating voltage. So you see that when the energy of the X-rays is very high, that is, if nu is very high, then of course lambda will be much smaller for such X-rays, and then of course the mu absorption will decrease. So we shall notice a decrease in the value of the mu absorption with the increase in the value of the X-rays. which is what you can notice in this region, where the absorption coefficient is going to decrease. So you see that in the today's lecture, I have explained the fine structure of the X-ray spectra, and I have also discussed in much greater detail the X-ray absorption spectra and how the edges are obtained and what is the meaning of the edges. The edges are actually explain the shell structure and the subshell structure of the heavier atoms. That is the structure of the atom. The structure of the shells and the subshells is explained using the fine structure of the X-ray spectra and also through the absorption spectrum of the X-rays. The lecture is continued, but this is the end of this lecture. That is the end of slide number 16C.